Algebra 1, Lesson 10.2. This is called Simplifying Radical Expressions. So here's what we have going on. All right, so first label, this is 10.2, simplify, oops. One of these days, I'm not going to have a problem like that at the top of the page. Simplifying radical expressions. So radical, again, meaning we have some kind of a root, a square root, a cubed root, a fourth root, etc. But in this context, we're just dealing with square roots. So we're going to use radical as a synonym for square root here. And we're simplifying them, which could raise the question, well, what does it mean for a radical expression to be simplified? And there are kind of three rules, basically, that we look for. So we'll say simplifying. Rule number one, no perfect squares left as factors of the radicand. And the radicand, again, is what is inside of the square root. So I'll say what's inside the root. Okay, so perfect squares, what we mean, perfect squares, technically I should say no perfect squares other than 1, because 1 is 1 times 1. So we're looking at all the perfect squares greater than 1. So we have, well, 2 squared, which is 4, 3 squared, which is 9, 4 squared, which is 16, 5 squared, which is 25, 6 squared, which is 36, 7 squared, which is 49, 8 squared, which is 64, 9 squared, which is 81, and 10 squared, which is 100. Okay, so what do we mean by no perfect squares left as factors of the radicand? Well, let's do one quick example of what that would look like. So let's just say you had simplify the square root of 300. Now, before I do that, though, I need to lay one other piece of groundwork about how multiplication and division works with square roots. This is kind of a little side note. We can say like note. I'll use 2 and 3 here. The square root of 2 times the square root of 3. Well, that's the same thing as the square root of 2 times 3. And that's the same thing as the square root of 6. Okay? And that works both ways. So you could say the square root of 2 times the square root of 3 is the same thing as the square root of 2 times 3, which is the same thing as square root of 6. You can also work that backwards and say, well, the square root of 6 is the same thing as the square root of 2 times 3. And that's the same thing as the square root of 2 times the square root of 3. So we're going to use that to our advantage here by saying, well, the square root of 300, well, that's the same thing as the square root of 100 times 3. Oh, well, the square root of 100 times 3, that's the same thing as the square root of 100 times the square root of 3. And we know what the square root of 100 is, because if we look up at this one right here, if 10 squared equals 100, then the square root of 100 equals 10. there are a couple different ways I could show that, but I'm going to rely on the fact that you've learned a little bit about square roots in past classes, including pre-algebra, and not take the time to go into why we're able to say that the square root of 100 is 10. So I can just say here, though, the square root of 100 is 10, so this leaves me with 10 root 3. And that's how we would write that. We don't bother to write 10 times root 3. We just represent it as 10 root 3. And so this would be the simplification of what we started with. And this is fulfilling rule number 1, that we don't have any perfect squares left as factors inside the radical. Okay? So 3 is not a perfect square. 9 is, but 3 in and of itself is not. And so there's no more simplifying that we can do to the root 3. But the 100 inside became 10 outside. Okay? All right, so that's rule number 1. Rule number 2. Rule number 2 is that there are no fractions inside the radical. No fractions inside the radical. And we're going to use a very similar thing to the yellow note up above. We're going to have a note like that here. Division works the same as multiplication. So we could say that the square root of 5/4 is the same thing as the square root of 5 divided by the square root of 4. Okay? So dividing numbers inside the radical is the same thing as the square root of the numerator divided by the square root of the denominator. Okay, and we can actually just use that note essentially as an example. We could say simplify, and maybe I'll change it just a teeny bit. Simplify, let's go with the square root of 7/25. And you do have to be careful with writing these, that you are very clear with what is inside the radical and what is not inside the radical. So for example, we need to be careful not to write it as like, because that looks to me more like that just the 7 is inside the square root sign. And what we're starting with here is that the whole fraction is inside the square root. All right, well, the square root of 7/25 I can rewrite as the square root of 7 divided by the square root of 25. And, 25 is a perfect square. Okay, so 25, we have that up there. 25 is 5 squared. So the square root of 5 squared is just 5. So this is the same thing as the square root of 7 divided by 5. So that one combined rule number 2 and rule number 1. Because rule number 2 was no fractions inside the radical. All right, well, we kind of accomplished that with our first step here. We got rid of a fraction being inside the radical. But then, according to rule number 1, we can't have any perfect squares left inside of the radical. And so doing the square root of 25, same thing as 5, that fixed it for rule number 1 as well. All right, so no fractions inside the radical. And sometimes, though, when you deal with rule number 2 kind of stuff, you'll run into rule number 3 of simplifying. Rule number 3. And it's this: no radicals in the denominator. So what if instead of 7/25 we had this? Let's say we had this. Simplify the square root of 7/3. All right. Well, so we can start out doing what we did in the previous step, which is rewrite it as the square root of 7 divided by the square root of 3. And this fixes rule number 2. But now we're running into rule number 3, which is no radicals in the denominator. So what do we do in this case? Well, what we do is we have our schmancy version of number 1, or the carefully chosen number 1, to the rescue again. Because when simplifying, I can do stuff like add 0 or multiply by 1, because adding 0 doesn't change the value of what I'm dealing with, and multiplying by 1 does not change the value of what I'm dealing with. So what I can do is I can multiply by, I'm going to take this denominator, and I'm going to use that as what I'm going to multiply. I'm going to take it as the denominator over the denominator value over the denominator value. So this is just equal to 1. So I'm not changing the value of what I'm dealing with. But watch what happens. By multiplying top and bottom by that root 3, what I get is the top, I get root 7 times root 3. All right, that's the same thing as root 7 times 3. That gives me just the square root of 21. But what's root 3 times root 3? Well, root 3 times root 3 is the square root of 9, which is just 3. And that is fully simplified now. I don't have any square roots rule number 1, I don't have any perfect squares inside of a square root. Rule number 2, I don't have any fractions inside the square root. And rule number 3, I don't have any radicals in the denominator. Okay, let's do a couple more that involve this rule number 3, because that's going to come up a variety of times. So let's do another example here. Let's say simplify. How about root 6/3? All right, we can do the same thing again. We can say that's the same thing as root 6 over root 3. And we can multiply top and bottom by that root 3. So root 3 over root 3. So what does that give me? That gives me root 12 over 3. Now with this root 12, I have to check again, do I have any perfect squares in there? And well, 12, I know is 4 times 3, right? So that's the same thing as root 4 times root 3. And I still have this over 3. Well, the square root of 4 is something that I know. That is 2. So what do I get here? I get 2 root 3 over 3. And that's as far as we can go. And it might seem like that does not seem simpler than what we started with, because now we have a fraction and regular numbers and square roots going on. But according to the mathematically agreed upon rules of simplifying radicals, that is more simplified than what we started with. Let's see. All right, a couple more examples. Let's say we have this. Simplify. Let's go with 5 over 3 minus the square root of 7. Well, this looks ugly. We're going to use something here called the conjugate. Conjugate. The conjugate of 3 minus the square root of 7 is 3 plus the square root of 7. The conjugate of the square root of 2 plus the square root of 5 is the square root of 2 minus the square root of 5. The conjugate of the square root of 10 plus 1 is the square root of 10 minus 1, etc. Okay? So the conjugates are when you have two terms like that, and one of them is minus and the other one is plus. That's all that's going on. Okay? Well, when we have a situation, actually move that one down, put that back where it came from. Okay, when we have a situation like this, where we have in the denominator two terms, and one of them is a radical, what we do is we multiply the top and the bottom by the conjugate of that denominator. So what that looks like is this. We have 5 over 3 minus the square root of 7. And what we're going to multiply is we're going to multiply the top and the bottom by 3 plus the square root of 7. We're going to go times 3 plus the square root of 7 over 3 plus the square root of 7. I can multiply by 3 plus root 7 over 3 plus root 7 because it equals 1. So I'm not changing the value of what I'm dealing with. But let's see what happens. The top we have, so we need to distribute because it's this 5 times this whole thing. So we need to use rules of distribution. So we have 5 times 3, that's 15, plus 5 times the square root of 7, that's just 5 root 7. Okay? Now the bottom. This is one of the many reasons why we learned about a difference of squares. You might recall, some of you will, some of you won't, but that's okay. That's why we are reviewing a little bit here, that this is the difference of squares. We looked at the difference of squares with things like, I'll just put over here, diff of squares. It first came up in the context of factoring, where we had stuff like factor x squared minus 36. And we factor that as x plus 36, x plus 6, square root, x plus 6 times x minus 6. Okay? And that's kind of what we have going on here. When we have 3 minus root 7 times 3 plus root 7, this is why we use this to our advantage. I mean, I could go ahead and show the full multiplying out. So we have distribution here as well. We have to FOIL this. So we have 3 times 3, that's 9. And we have, so that was the 3 times 3. Then I can do the 3 times root 7. So plus 3 root 7. So I use this first 3 both times. Now I have this negative root 7 times 3. That gives me minus 3 root 7. And I have this negative root 7 times this positive root 7. That's going to give me minus root 49. Okay? Well, the plus 3 root 7 and the minus 3 root 7 cancel out. And that's why difference of squares goes from something over here that looks like it should multiply out to be 4 terms, but it actually, or 3 or 4, but it actually only multiplies out to be 2 terms because you always have this canceling that happens. So what we're left with then is we are left with, so I still have the top going on, 15 plus 5 root 7 over, and what do we have now? We have 9 minus the square root of 49, which is 9 minus 7. All right, well, that leaves me with 2. So that gives me with, I still have the 15 plus 5 root 7 over 2. And that is as far as we can go. The one other thing we should check for is we should make sure that this radical here does not have any perfect squares in it, and it doesn't. Square root of 7 doesn't have any perfect squares. And let me rebox that. We should also make sure that this fraction does not simplify. In other words, we have 15 halves as the first half here. 15 halves, and that doesn't simplify. And we have 5 root 7. Oh, oops, wrong thing. Sorry. Let me undo that. Okay. We have 5 root 7 over 2, and that does not simplify. What would simplify if we ended up with something like this? Let's just say we ended up with, I'm just going to go with totally different numbers here. Let's say we ended up with 8 plus 10 root 7 over 2. If we had that, we could rewrite this as 8 over 2 plus 10 root 7 over 2. So again, when you add fractions that have the same denominator, the numerators combine and you have just the one denominator. So I'm just splitting this back out as two separate fractions. Well, 8 over 2 is just 4. And the 10 over 2 here leaves us with a 5 root 7. And that would be the simplification of what we started with right there. Okay? All right, so that's that tool, is when you have two terms in the denominator, like this, and one of them is a square root, you simplify by multiplying the top and the bottom by the conjugate of that denominator that you have. Okay, that's that kind. All right. We also, well, another example of not necessarily this, but something that might trip some of you up. What if we had something like this? Simplify. Let's go with 5 root 6 times times 2 root 3. All right, now this is technically just a bunch of multiplication, as in we have 5 times the square root of 6 times 2 times the square root of 3. And if it helps, you can rearrange, because when you're just multiplying a string of things, you can multiply them in any order and you get the same thing. So if it helps, you could rewrite this first as we have 5 times 2 times the square root of 6 times the square root of 3. All right, well, the 5 times 2, that's just 10. And the root 6 times root 3, that's root 18. Now we need to look for any perfect squares that we have inside the radical. Well, 18 is 9 times 2, so that's the same thing as 10 root 9 times the square root of 2. Oh, root 9 is 3, so that is the same thing as 10 times 3 times the square root of 2, which all of that becomes then 30 root 2. And that's as far as we can go. It looks very different from what we started with. We didn't have a square root of 2 to begin with. I mean, it's kind of hidden in here. Oops, I didn't mean to do the eraser. It's kind of hidden in here because 6 is 2 times 3, and then we have another 3. So what do we have going on inside the square root? So you have 2 times 3 times 3. So that's why we had a 3 come out, and we're just left with the 2 inside the square root. All right, so there's that kind. Then you also sometimes might deal with some that have some variables inside. So it might be something like this. Simplify, let's say square root of 50 x squared y to the 5th z to the 10th. All right, let's see what we can do. So again, simplifying, we are wanting to pull out any perfect squares. Anything that is something times itself. Anything that is something times itself can come out. So let's see what we have. Well, the square root of 50, that is the square root of 2 times 25, right? And 25 is a perfect square. It's 5 times itself. So since we have 5 times itself inside a square root, that can come out, but we'll deal with that in a second, so I need to make sure I represent everything that I'm still dealing with in this line. You don't have to simplify or split it out like this, but it's just how I'm doing it. I'm splitting out each in the numbers versus the x's versus the y's versus the z's. So then we have square root of x squared. Oh, well, x squared is x times x, right? It's x times itself. Okay, so we're going to have some simplifying there. Then x to the fifth. I'm sorry, y to the fifth. Y to the fifth. Well, I could rewrite this as y times y times y times y times y, right? In other words, y to the fifth is y times itself 5 times. Well, I can also rewrite it as y to the fourth times one more y, right? Or if you prefer, I could write it as y squared times y times y. Be the same thing as like y squared times y squared times y. Okay. And I'm going to leave that there just for a moment. Well, no, let me go ahead and park here. Okay. So y to the fourth, maybe you're okay with just saying, oh, the square root of y to the fourth is y squared. Looking at this line here, that the y square root of y to the fourth, that would leave you with a y squared outside the square root, and you're still left with this y inside. Or if you prefer, you could look at it as anything that is something times itself comes out of the square root. So here we have a y squared times a y squared. That would leave us with a y squared outside the square root, and we're left with this y inside the square root. That's another way of looking at what's going on. Another way of looking at it is the textbook doesn't technically get into this at this point, but the square root of something is the same thing as raising it to the power of 1/2. In other words, the square root of 3 is the same thing as 3 to the 1/2 power. And whenever you get fractions as exponents, you're technically dealing with roots. Well, that's another way of saying that, like, z to the 10th, the square root of z to the 10th, that's the same thing as z to the 10 halves power. Taking a square root gives us a halves as the exponent. Well, what is 10 halves? But that's the same thing as z to the 5th. So a z to the 10th inside can become a z to the 5th outside. We cut it in half. Okay? Same thing like this square root over here, this square root of x squared. Square root of x squared, you can cut the exponent in half, and it comes out. In other words, an x squared inside becomes an what's half of 2, but 1, becomes an x to the first outside. Here we have y to the, I was on the eraser again, sorry. Here we have y to the 5th. Well, square root of y to the 5th, that's the same thing as the square, sorry, not square root. The square root of y to the 5th is the same thing as y to the 5 halves. Well, what's 5 halves? So we say square root of y to the 5th, that's the same thing as y to the 5 halves. Okay. Well, what's 5 halves? Well, one way of looking at it is it's y to the, what is that, 2.5? 2 and 1/2? Okay. And because of the, hold on a second, I gotta get a power cable. I thought I had enough juice on my laptop, but I don't. And I'm getting a notification that my battery is just about to die. All right, so let me grab this. So this will be a really brief interruption. Sorry about that. Thankfully, I had one fairly close by. And good to go. Oh. Screen only two, so I was okay. 2 and 1/2. That would become a y squared times the square root of y. So this y squared comes out. And then this y to the 1/2, this y to the 1/2 becomes our square root of y. There are multiple ways of viewing this. Sometimes it's hard to know when just to explain something one way and be like, this is the way to view it, versus explaining it multiple ways and saying, whichever way makes the most sense for you, whichever way works best for you, you can go ahead and do it that way. Okay? All right, so that's all kind of side note stuff. I'm going to put that over there like that. And I'm going to erase this line so we can continue. Oh, I didn't do the z's. Here we have times square root of z to the 10th. Okay, so again, square roots cut the exponents in half. And the same does work for numbers, just like this square root of 25, well, that's 5 squared. A 5 squared inside becomes a 5 to the 2 halves outside, which is just 5. 5 to the first. Okay. All right, so what are we left with here? We're left with 5 root 2, right, times x, because square root of x squared is x, times y squared root y times times z to the 5th. And then how we like to write these is everything that is outside of the square root first, and then everything that is inside the square root all together afterwards. So what we would have is we would have 5x y squared z to the 5th. So I used everything that's outside of the square root. Root, and what's inside? 2y. And that's what we would have. Now, technically, there's some absolute values that should go on here, but I'm not going to require you to do that. But here's something that technically you should do as an extra step when you're looking at these. You should look and see, all right, well, what I started with can only spit out positive numbers. But for this x here, x squared, well, let me take a step back, can only spit out positive numbers because when you're dealing with real numbers, you can only have positive values inside the square root, and the square root can only spit out a positive answer. As soon as you start to have negatives inside of square roots, then you're dealing with imaginary numbers, and that's something we're not getting to yet. But because this x is being squared, I could plug in a positive number for x or a negative number for x. Let's just say x is, if we had the square root of x squared, okay? If x is -3, that'd be the square root of -3 squared. Well, that's the same thing as the square root of 9, which is 3. Or x could have been a positive 3. Positive 3 squared, that's the same thing as square root of 9, that's the same thing as 3. So x could have been positive numbers or negative numbers. But whether x was positive or negative, we only got positive answers. Okay? And so you're supposed to check to make sure that you keep the same situation at the end as you had at the beginning. What we started with is you can plug in positive or negative values for x, and you only get positive answers. Well, if we look at where our x is here, here's our x. Am I allowed to plug in positives or negatives? Yes. If there's just an x hanging out like that, I can plug in a positive number or a negative number for x. But if I plug in a negative number for x, it now makes my whole answer negative. And that's not what it did before. So the way that we fix that is we put the x in absolute values. What it does now is it still allows us to plug in positive or negative values for x. But even if we plug in a negative value for x, we will still get a positive answer like what we originally started with. That's a brief explanation of what's going on with absolute values. The same thing is actually happening with the z's. If it's what we started with,
what we started with, we could plug in positive or negative values for z, and because we were raising it to the 10th power, we would end up with positive values always. But what we have now with the z's, because the z's now have a 5th power, if we plug in negatives, we would get a negative answer, but that's not consistent with what we started with. So we should put the z in absolute value as well. The y's, we don't have to, because what we started with for the y's, y to the 5th inside the square root meant we could only plug in positive values for y. If we plug in a negative, because it's an odd exponent, we would end up with a negative number, and we're not allowed to have negative numbers inside the square root. So what we started with, we were only allowed to plug in positive values for y. And because of this y hanging out right here, we still are only allowed to plug in positive values for y. And so that hasn't changed. So what's inside the box right now would be your final answer if you did stuff with absolute values, but I'm not going to require that. All right. That should get you pretty well ready for doing this homework. Let me just double check your homework sheet and see, yeah, maybe we should do one that is kind of like that. That's the only thing left that I see. Okay, let's do one like this. Let's do one, this will be our last example. Example, simplify square root of, let's go 7/5 times the square root of, how about 5/6? No, I don't want to go 5/6. Let's go 11/6. 11/6. All right. Nope, I don't like that either. I'm going to change this denominator. Let's go, let's go tenths. 11/10. Okay. All right. Well, we're multiplying two different values, right? So we can combine this all into one. So you could say what we have is we have this is the same thing as the square root of 77/50ths. Okay? And well, that is the same thing as the square root of 77 over the square root of 50. Okay? Well, that is the same thing as the square root of 77 over the square root of 2 times 25. Okay? Well, the 25 inside can become a 5 outside. That's the same thing as the square root of 77 over 5 root 2. But now we have that rule number 3. We have a radical inside the denominator. So we fix that by multiplying top and the bottom by root 2. So root 2 over root 2. Okay? And that will give us 77 times 2 is, well, 70 times 2 would be 140, right? 140. But then we have that 7 times 2, 14, so 154. That is root 154 over 5 times 2, because square root of 2 times the square root of 2 is 2. And then finally, this gives us root 154 over 10. And that is as far as we can go there. Okay? All right. Hope that helps. Pop into an office hour or shoot me an email if you have any questions. And I hope this goes well. Thanks.